Multiverse.
Can you guys hear me okay?
Yeah, there's some echo, but should be fine.
There's an echo. Oh, that's weird.
No, it's fine.
Huh?
Now it's better.
Is it okay?
Yeah.
Let me see.
So probably it's your Sokoko.
Can you guys hear me okay?
Oh, there's a little bit of echo, I think.
Do one more thing, sorry. Guy, can you hear me okay?
Yeah, it's fine.
Okay, great.
Yeah.
All righty. Shall we get started?
Yeah, please go ahead.
Okay, great. Well, it's been really terrific to at least hear 2 of the days of these talks. I was away on Monday. There's lots of very, very cool stuff happening. Thanks very much for the invitation to say a few words. Really what I want to do is just talk about a few, I think, interesting, open, conceptual questions, all along the lines of how much of the physics that give rise to the cosmological correlators that we measure on the future boundary can we actually extract from these measurements that we make only on the boundary? And I think this question was asked at various points earlier in the meeting. Why do we care about the sort of pure boundary description of the physics? Isn't what we're really interested in to figure out what happened early in the history of the universe. So just the zeroth order question is, why do we care about formulating physics in this way? The most obvious answer is that none of us were around in the early history of the universe. That entire early cosmological history is a kind of a story that we make up, a rational story that we make up in order to explain the pattern of spatial correlations that we see in the present. That's true of any historical science. It's not like, that's why cosmology is observational rather than experimental. It's not even like, for example, the physics of scattering amplitudes, where we can imagine doing the experiment over and over again, even though we don't follow the particles in the trajectories in to see what happens to them as they bang into each other and come back out. We can still imagine doing the experiment over and over again. Here we can't even do that. We're stuck out in roughly infinite future, and we see a bunch of pattern of correlations in the present, and we infer the existence of a cosmological history to explain it. And the sort of most highfalutin reason, the sort of pretentious reason for trying to think purely in terms of these boundary observables is that ultimately we know that picture of time evolution has difficulty. It breaks down ultimately when we talk about what happens near the Big Bang, at the very least. So that's some indication that we should try to eviscerate the picture of sort of time evolution from our picture of where these correlations come from. And if we do that, the only thing we have left is to try to understand somehow some set of rules, some principles directly formulated on the spatial future, which gives us exactly the same answers as what we ordinarily ascribe to coming from time evolution. Of course, if we find out what that picture is, one thing it should do is tell us why, at least in some approximation, it looks like it comes from time evolution. So that's the sort of absolute deepest reason to try to be doing this. Cosmology is the place where all the questions about emergent space-time, maybe even extensions of quantum mechanics, ultimately when we try to deal with the multiverse, But anyway, cosmology is a place where those things have real teeth, and they're really forced on us. Of course, there's a more pragmatic reason that we do it, which is simply that when you actually do the calculations using the standard picture of time evolution, you get lots of complications and intermediate results that cancel in the final result. Very much, again, like the story of what we've seen in scattering amplitude. As we've discussed a number of times, and I'll say a little bit more about in a second, cosmological correlators contain scattering amplitudes. I think that's an absolutely amazing thing that this totally static observation that you do on this late spatial slice with some analytic continuation actually contains all the dynamical information about in and out states and particle scattering. So all of the tremendous simplifications seen in the sort of on-shell way of thinking about scattering amplitudes must be reflected somehow in cosmological correlators as well. So that's a practical reason for thinking in these boundary terms, is it makes the calculations not only easier, but also one can hope starts bringing out some hidden structure. So there's then sort of two roads that we can take. We can take them simultaneously. They're very much compatible with each other. One of them is to try to understand what the rules are. How precisely should we, purely from boundary considerations, set up in order to make sure that we are compatible with the principles that we know are there: locality, unitarity, causality, and so on. Again, very, very analogous to what we do with amplitudes. And how can we use symmetries, singularities, other principles in order to completely determine the answer, eschewing any picture of bulk time evolution. So that's kind of a responsible thing that we can try and do. A more irresponsible thing that we can do is to actually try to guess some structure that actually gives us those answers from an answer to a completely different kind of question. We've seen examples of that in working in some detail in the story of scattering amplitudes. These general notions of positive geometries that live in one way or another in the asymptotic, in the kinematic space that defines the amplitudes. So those are objects that have no reference to a Hilbert space or space-time or anything like that. You ask a sort of simple combinatorial geometric question about them, and the answer ends up giving you something which has all the properties that you ascribe to local and unitary evolution, at least in the examples that have been understood. We have only very baby examples of that in the context of cosmology, and in the story you heard already from Paolo about the cosmological polytopes. I won't say much more about that direction here, mostly because that there's a next that needs to happen, which is to figure out how to go beyond single diagrams and understand what geometric objects might be that put all the diagrams together. And there's all kinds of zeroth order sort of obstacles that are easy to overcome, but there are some sort of heart of the matter that needs to be figured out. And just from experience, I can say this is not the sort of thing that benefits that much from discussion. You just have to do it at some point. So this is, I suspect it will happen. I hope it'll happen at some point, but anyway, I won't be talking about that. Instead, I will talk more about a few conceptual questions related to how we understand some basic qualitative features of cosmological history purely from the boundary perspective. So there are sort of four questions that I want to talk about, and I'll be pretty brief, but let me first go through the questions. First, how can we see history or time evolution purely from the perspective of boundary correlators? That's an obvious, interesting question. Secondly, it's all very well and good to talk about these boundary correlators, but you say, surely, look, there actually are local, at least in some approximation, there are local quantum fields. There is a bulk, there is time evolution, and so on. How can I see that? How can I see that these correlators are actually, how can I more explicitly start from the correlators and build objects that I can identify as local bulk fields, satisfying local equations of motion, and so on? How can we do that from boundary correlators? And here, I'm not talking, I should stress, we'll be talking mostly in the context of perturbation theory. So this is not some highfalutin thing about how we see approximate bulk locality in ADS from CFTs with large gaps, blah, blah, blah. This is someone hands you the correlators, and from this information, you want to build something that looks like a bulk space-time field labeled by an X and a T, and see that it satisfies local equations of motion. How do we see that? How do we see that the correlators are actually associated with local bulk fields? There's obvious issues associated with that. It can't be unique, but anyway, I'll say a little bit about that.
Is this some analog of there?
And related to that, going one step further, can we even in principle see the physics associated with the Big Bang singularity or whatever resolves the Big Bang singularity in correlators? Okay, so those are the four things I just want to say. I'll say a little bit more about the first 2 points and just some more qualitative comments about the last two. But maybe I pause here. I doubt there's any questions because I haven't said anything yet. But so far so good.
I wanted to ask if the point about local fields, is it something? Are you trying to find something similar to HKLL?
No. You'll see what I'm trying to do. You will see what I'm trying to do in a moment. I want to actually see how I won't give the answer for correlators. But I'll sketch something that works for amplitudes, and I want to see what the analog of that is for correlators. In other words, what I want to see is just the rough idea is that amplitudes and correlators are sort of on shelf, and there's a canonical there's a way of lifting them to off-shell objects. It's not unique what the off-shell objects are, but it turns out that every way of lifting them to off-shell objects satisfies local equations of motion. And the different ways of lifting them to off-shell objects correspond to field redefinitions of the underlying local theory.
Sorry, Nima. Now I'm confused by what you're saying because as we discussed a little in chat as a sanity check, since you're working at a perturbative level, you're not trying to do everything here. If I give you a state, you can check if it's consistent with local evolution that leading up to it. But you could give me a state and I could declare that I'm going to involve it forward or backward in time with a non-local Hamiltonian. Nothing can stop me. Nothing can stop me from doing that. So I don't see how anything could imply that it had to have come from.
So this is actually not what I'm saying here. What I'm saying something more limited. I'm saying, how do you start from some sort of on-shell object and lift it to something that you can interpret as a bulk field, labeled by a point satisfying local equations of motion? Of course, you could have some crazy things in the middle. It's not saying that that's the only thing that could give rise to this on-shell object, but it's a natural way of going back and forth from the on-shell to the off-shell object.
Okay, good. So you're speaking to what extent that's unique, if you even stipulate that it had to have come from.
It's trivial. At free level, it's just any way of lifting something for amplitudes, removing the mass shell condition. So I'm just saying slightly more here at the level of an interacting theory.
Okay, thanks.
All right.
But Nima, why the answer is not just using
so let's start with the first topic.
Nima, can I ask why the answer is not just using the formula I just showed earlier on, this asymptotic formula near the boundary of the sitter, and then plugging in the correlators? This gives you a local formula, satisfies Einstein equations.
Maybe you can come back to, why don't we come back to that comment when you, let's have that discussion when we come to it, okay? So, Okay, so let me first talk about how we see history. And I think, to me, one of the most interesting things is if we talk about this sort of 4-point function. If we talk about the 4-point function, and let me define these sort of usual variables that we've been used to talking about. Okay, so then something that we've seen, at least in de Sitter, is that time evolution is associated with the fact, not just overall, we're used to the fact that overall scale is overall time in the ADS, but we have the sort of more interesting fact that we have that if we have an S-channel process like this, that time evolution means that there's an ordinary differential equation that this function satisfies. So we have an equation that looks like some second order operator delta x plus mu squared acting on f is equal to 1 over x plus y. Okay, now, I find this extremely interesting because you're really seeing a history by keeping two sides of this quadrilateral fixed and just seeing that there is actually a second order equation that's satisfied as you increase the side length of the other two sides of the quadrilateral. So in other words, it's this differential time shows up as the fact that this correlator satisfies this interesting second order differential equation. And it's a kind of a specific kind of differential equation. Of course, we've seen this before. This is the analog for amplitudes of the fact that if I had an amplitude sitting here, then I would have P1 plus P2 squared minus m squared acting on the amplitude would, in this case, would equal a constant. So again, this is an equation of motion, and it looks like this is the analog of the sort of the equation of motion for the amplitude. I want to say it maybe slightly more generally, is that in these cases where we have some perturbative picture of the physics, this is more generally some simple operator on something with a more complicated analytic behavior is equal to a simpler analytic behavior. So in this case, it's pretty simple, but the more complicated analytic behavior is the fact that this guy has a pole. The simpler analytic behavior is the fact that it doesn't have a pole, so it's just a contact interaction. And so a time evolution or local evolution in the case of amplitudes is reflected by the fact that it's possible to hit the amplitude, which is complicated by a simple operator that makes its analytic structure more simple. And that's exactly what's happening in this example, is that we have now a relatively complicated function of k's, but there's a simple differential operator that when you hit when you act on it, when you act on the correlator with it, you get something with a much simpler sort of contact-like analytic structure. So one question is, how general is this? So here we got this from conformal symmetry. Okay, here we got this. One way of getting this differential equation is from conformal symmetry. Another way of getting the differential equation is directly looking at the bulk calculation. So if you look at the bulk calculation, then you find there's some way of acting with differential operators here on 1 and 2 that collapses the internal propagator and gives you just something that looks like that. Okay, so here we have a bulk picture that gives us a differential operator. We have the sort of boundary picture from conformal symmetry that gives us the differential operator. But I want to stress that we could actually have gotten this differential operator even if we didn't have the bulk picture and even if we didn't know about conformal symmetry. So how does it work in this example? This is actually it's an illustration. So let's work with let's just work with conformally coupled scalars for a second in this toy model, conformally coupled scalars in FRW. And here the entire correlation function is given by for general, if we take any old graph, so let's say if we take any old graph at all, then we associate these energy variables with all the vertices, so on. And so we have this nice expression. It's possible to do all the time integrals, and the particular FRW background just goes in to, it's just represented by a certain Fourier transform. So this was reviewed quickly in Paolo's talk. So you add these energies epsilon1 through epsilon n to all of the vertices, and then you multiply by the wave function where the energies entering all the vertices are shifted by these epsilons, and the intermediate guys are unshifted. Okay, so this is of course we can get this from the usual time evolution picture, but I want to stress that this is an equation for the wave function where now the information about FRW of what background you have, it just goes into these G tildes. And this object psi you can compute in various ways, but one nice thing is it has its some sort of ab initio definition as the canonical form associated with these cosmological polytopes. So this is just to say there's some expression where you can put in the freedom of any FRW background that you like, which gives you the answer with no time integrals seen anywhere here. That's the point. So okay, so now so the sort of particular case of de Sitter is when all these G tilde of e's is just equal to 1. So let me just illustrate then what's going on. So if we look at this example, then exactly. So I'm going to say X is the sum of the energies here, Y is the sum of the energies there, and so we have some function of this of our capital X and capital Y variables that looks like f of capital X and capital Y is dx dy over. So this little x is the shift. I've scaled the internal energy to be 1, so that's where the 1 is coming from. Okay, so this is what we get for this conformally coupled scalar. And okay, this is, you can integrate this and get some dialogues, right? But what I want to stress now is why you can see that this thing satisfies the second order differential equation. What you're looking for is some way of hitting this with some differential operator f to make this simpler. And as it is, this guy has branch cuts. It's a polylogarithmic. It has branch cuts when x plus 1 goes to 0, y plus 1 goes to 0, x plus y goes to 0, and so on. And you can see that from the fact that this integrand has non-vanishing residues at those places. So what you want to do is apply a certain differential operator just acting on the external states on f so that you kill all of those non-trivial residues. If you kill all of those non-trivial residues, you guarantee that the function you have on the right-hand side cannot be transcendental. It can only be rational. Okay? And so that's a simple exercise. So you just you just take any a dx squared plus b dx, and you act on f, and you just ask for the residues to vanish at x equals minus x minus 1, or y equals minus 1 minus y, and so on. And if you do that, you find there's a unique solution, and the unique solution is the guy that we want. Okay, so from here, you discover that delta x is exactly 1 minus x squared dx squared minus 2x dx. So no imagination, no thinking about conformal invariance, but the sort of general philosophy that that evolution is reflected in equations that hit the object that you're interested in and make it less complicated, make its analytic structure less complicated. So in this case, we are taking something and which had branch cuts, and we found a differential operator that removes those branch cuts and gives us something rational. And it's interesting that the operator that does that is the operator that also is interpretable as this sort of time evolution picture where you keep two sides fixed and you increase the length of the other sides. So that's, I think, an interesting general question. Can we do that for a more general background? So we already in this example, we can try something slightly more general. For example, if we had a power law rather than strict de Sitter, we would be looking at an equation where we just add x to the epsilon, y to the epsilon out front. Okay, and so but more generally, the question is, if we have these g tildes here, is there some way that we can directly is there some way that we can extract what these g tildes are, learn something about them, or even something sort of qualitative about this representation of the correlator by acting with a certain kind of operator on the 4-point function? Okay, so okay, so that's the sharper version of this question. Can we see time evolution in the correlator? Is there and how can we find in general some kind of operator that we hit on the 4-point function that simplifies its analytic structure? And the point has got to be that that operator has to depend on the choice of background. So you would hunt around until you find some operator that that simplifies the analytic structure, and you'd have to make a different choice for the operator depending on what the background is. Let me just give you a very quick example of a very quick toy example of how this works, just to sort of illustrate what the idea is. So instead of doing this example, which is slightly complicated, it's a 2-dimensional integral. Let's do this example. So let's say it's just a 1-dimensional integral, but it looks kind of more or less the same. So if I had something like this, then I'd log x out of this. And I know what I would do. So if this is my function, then the operator that simplifies its analytic structure is x ddx. So x ddx f is 1. Okay, so that's the analog of what we had before. But what if we have a more general background? So what if we have something that looks like the analog of what we did before? What if we have some x to the epsilon here? Well, of course, in this case, it's trivial to do the actual calculation, and you get x to the epsilon minus 1. Let me call it over epsilon hat. Epsilon hat is just pi over sine pi epsilon, basically 1 over epsilon for small epsilon. Okay, so that's what the actual function looks like. It still has a branch cut at x equals 0, just like the log does. And again, we want to know, is there an operator that we can hit that simplifies, that removes that branch cut? And that'll be the sort of that'll be the equation of motion. That'll be the sort of time evolution equation for this guy. And of course, so in this case, in this case, it's trivial. In this case, you get x ddx f minus epsilon f is equal to 1. Okay, so that's so if f is equal to x to the epsilon minus 1 over epsilon, then that's our differential equation. So it has to know about epsilon. But actually, things get a little more interesting if this was, if you like, in the case where our g tilde x is just 1 power of x. what if it's a sum of many things of this form? You know, sort of some a1 x to the epsilon 1 plus dot dot plus an x epsilon to the n, the point is very simple. So in this case, the actual f turns out to be, of course, just the sum of all these things. But you can very easily see, that if I take x dx of f, if I take f, let me just remove these constants plus the sum of ai over epsilon I. Let me call this guy f hat. So if I take f hat, if I take f hat x d dx of f hat, x d dx squared of f hat, and so on, then these are just, this is just the sum of 1 over epsilon I, x to the epsilon I. This is, the next one is just the sum of x to the epsilon I, ai. The next one just brings down powers of epsilon. And the point is that these are just linear combinations of exactly the same powers of x to the epsilon I. So if you keep n powers, but you keep n plus 1 of these derivatives, there's a linear relation between them. Okay, so there's a differential equation that annihilates this guy, there's a differential equation that annihilates this guy. But as you keep more and more powers of epsilon, the differential equation gets bigger and bigger and bigger. The order of the differential equation gets larger and larger and larger. So I think that's so it's likely the case that the structure of this operator that for a general background, the structure of this operator that simplifies the answer, if it exists, it's not going to just be purely local in energy. As we see in this example, when I include more and more powers of x, I have to include higher and higher derivatives. What's hopefully the case is that it has some memory in the energy, which doesn't go back arbitrarily far in time, arbitrarily back in energy, if you like. But when we're sort of close to something scale invariant, it's approximately local in the energy space. But this very simple example shows that that it's not guaranteed to always be second order, but that hopefully there's some systematic way of improving what this equation looks like that simplifies the analytic structure of the answer to incorporate a general background. And again, the sort of idea would be that if someone just hands you the correlator at some complicated analytic function, it's not at all guaranteed a priori. There's some way of hitting it with some kind of operator to remove the branch point singularities. And the operator which does that tells you about the background. Okay, so we've seen this in the simplest examples. In the de Sitter example, we know it's a second order operator, and there we happen to know that it comes also from conformal symmetry. But the general idea that time translations, that time evolution in the bulk should be reflected as some kind of evolution equations for the correlators on the boundary. If that general idea is correct, then we should see evidence for it beyond the cases where it's just controlled by symmetries. And I've given you a 20 examples like that happening. It would be interesting to try to understand what these operators are already in this simplest example of the conformally coupled scale. All right, so that was my first thing. I think I'm really going very, very slowly. So let me actually let me actually skip the second topic. We can chat more about it. I'll skip seeing local bulk physics. I just want to make we can come back and talk about it. I want to make just a few qualitative comments about the question of UV completion and something.
Sorry, Nima, can I ask you a question before you move on?
What kind of access we have to even in principle, what kind of access we have to things like the resolution of Big Bang singularity. Yes, is there a question?
Yeah, sorry, I had a question about your previous point, if I may.
Yeah.
So, yeah, this is more of a like a maybe foundational question. So, why do you expect that there should? I mean, the physics is not local in momentum space, right?
Right.
So, why do you expect that there should be a local operator that acts on these correlators and give you something?
Only because that's kind of what we've seen, and only because it is reflecting a qualitative part of the physics of inflation. So we know that overall, I mean, in other words, none of this is going to be true for totally random FRW backgrounds. So I'm really interested in things that, and of course, we can just do perturbation theory around de Sitter, but I'm sort of curious whether we can understand things from this point of view. If we, like, let's say, talk about just power law inflation, where I put some epsilon in there. Instead of doing it in an expansion in epsilon, whether there's something sort of exact that we can say even at finite epsilon. But the reason,
well, I mean, it's
overall scale in overall k is overall time, and we see that sort of relative k is relative time. So that we see in examples just at tree level. It is true, right? That's how it works in the 4-point function examples that we've seen, that when k's are very separated from each other, it corresponds to events that are very far apart. In the squeeze limit, for example, there are things that are far apart in time during inflation. So that's the sense in which some locality in k space seems to have something to do with locality in time during inflation. But really,
I was thinking more something about you could in principle. So you didn't have to like consider those specific kinetic terms. You could, I mean, if you want to like go whole hog, I mean, why not like considering the time dependent the speed of sound or a generic kinetic term?
Yeah, no problem.
But I mean, I was wondering what is the like invariant feature of this philosophy that will remain the same? So would you expect that?
I think the invariant feature is that when we have something like an exchange diagram, we know from the whatever the background is, we know that there's a limit where we make one side, when we make two sides much longer than the other, that does look like long separation between the two events in de Sitter. So that would make you think that there should be some autonomous kind of autonomous equation, differential equation or otherwise, that tells you about evolution in one pair of the variables, or another one, or you could keep 1 and 2 fixed, look at an equation in 3 and 4, and the fact that we have these sort of two, if you like, ordinary differential equations in these two different variables is describing the same history from the perspective of the two different vertices in the bulk. Okay, so that's what we've seen in examples in the neighborhood of de Sitter. The sort of general mathematical question is that we can define this wave function for any old FRW background, where the information about the background goes in this function g. So the question, I just practically want to compute this guy even. We know that finding these differential equations is a much more effective way of actually doing the computation than trying to do the integrals. Okay, so that's just at the most practical level. If you give me some g, how can I find the analog of these differential equations that sort of hit the object and turn it into something simple? Okay, so that's what I'm trying to sort of abstract away from our examples. That time evolution, at least in perturbation theory, time evolution is somehow reflected by the ability to, for amplitudes, for de Sitter wave functions, and perhaps beyond, it's reflected by the ability to hit the correlators with some interesting operators that simplify them. That's if I handed you a random function with branch cuts, it's not a priori obvious that you could do that. So it would be interesting to see if we can do that, and if it's a more general thing rather than just things that are forced on us by symmetries. So is the philosophy more clear?
Yeah, it is clear. I have more practical questions, like when you have higher order derivatives.
Yeah. I mean,
How many?
yeah, so
How many?
all of those things will add extra. I should stress this. All those things will add some extra numerators and some extra interesting structure. But at least for simple things in the neighborhood of massless fields or conformally coupled fields, the structure of these denominators, what the poles are in energies, how those poles can come together, is that's quite universal. So it can be dressed. They can have powers of the poles. You can have numerators, but the sort of pattern of the poles and how they come together, that's reflecting. That's a zeroth order thing. That's reflecting consistent time evolution in the bulk. And beyond that, I'm trying to see at the level. So at the level of the integrand, if you like, this energy integrand, we know what we're looking for. We know what pattern of poles are allowed and not allowed. I'm trying to see at the level of the actual answer how this is reflected. And I'm saying that there's very sort of concrete, simple questions where we can try to see whether something like this actually happens. So that's a very
Thanks for the clarification.
concrete question. If you give me some simple g of epsilon, what can I do with this integral? Is there some way of simplifying it? And I think there is something conceptually interesting about the fact that it's possible to simplify. And to remove all its branch cuts by these interesting differential operators, which in other examples are also what we think of as reflecting correctly time evolution. Okay, so I mean, even forget an amplitude. I mean, just something absolutely trivial. When you look at box phi equals j, phi itself is j over p squared, but box phi is now something which is free of poles. Okay, so the sort of fact that we have more complicated functions that are coming from solving some simple equation is the idea I'm trying to look for more generally for any backgrounds. And I just wanted to stress that we don't need the bulk picture, at least for the simplest case. We don't need the bulk picture, and we don't need conformal invariance to discover this differential operator. It really comes out directly from this attitude of trying to find something that removes the branch cut, remove the branch cuts associated with the function. All right. So yeah. So let me just say a few comments about these last points. So how do we see UV completion? Well, there are many aspects to this question, but I'll just mention one of them. This may well have been discussed earlier in this workshop. I'm not sure, but I'll just say it. So we know that when we look at cosmological correlators, that there's a limit where when we send the sum of all the energies, when we analytically continue, so the sum of all the energies goes to zero, that's dominated by when the sort of center of mass of all the time coordinates in the Feynman diagrams goes off to minus infinity. And so we have this claim that the leading singularity of the correlator as k total goes to zero is the high energy limit of the amplitude. So that's that's a very, very beautiful connection between correlators and amplitudes. But I just wanted to make the I think well known to many of you comment that in fact if we have gravitational theory, which we do, in fact all these singularities are gone. They're not actually there, and it's a very simple reason. So schematically, when we have what's going on is we have some integral that looks like this. And okay, we have some function of eta here. And if I put f of eta equal to 1, if I do this integral, I just get 1 over E total. Now, if f of eta isn't 1. But let's say, eta goes to minus infinity is the sort of ultraviolet here, the high energy limit of the flat space amplitude. So let's say f of eta goes like 1 over 1 plus, I don't know, eta over some eta naught to a power. Then I won't get 1 over E total anymore. But, so in other words, I won't get a pole at, so this is now in the E total plane. I won't get a pole at E total goes to 0, but I will get a branch cut at E total goes to 0. And so, for example, there's some sort of scale here set by 1 over eta naught, some ultraviolet scale. But if I'm far from there, you would think I do this sort of contour integral around the origin, and I get 1, 2 pi I, or 1. So you think that completely reliably from a calculation very far away from the sort of ultraviolet scale, I conclude that that there is a singularity at the origin, and fine. And there's a formula for the amplitude or the high energy limit of the amplitude in terms of the discontinuity at that point. However, when we have gravity, we know that the high energy amplitude does not behave like a power law. And in fact, the high energy amplitude, so instead of getting something that looks like e to the I E total eta, f of eta will actually go like e to the negative eta squared with some coefficient. Ultimately, 2 to 2, if we're talking about a 2 to 2 amplitude, ultimately 2 to 2 amplitudes are exponentially soft because you make black holes and so on and so forth. That's a qualitative difference between field theory and gravity. And that means that there is no singularity at all as E total goes to 0. Okay, so it's just kind of a very simple and basic point. It's exactly the same point as the absence of the so-called bulk point singularity in ADS-CFT. It's exactly the same thing. And the reason is very simple. The reason we have poles in E total before, in our previous examples, is that this integral is badly behaved if E total, has a negative imaginary part, for example. It would blow up. So that makes it clear it has to have a singularity when E total goes to 0. Okay, but if f of eta at large eta actually behaves like a Gaussian, like this, or in fact anything that beats e to the minus eta, then it doesn't care at all about E total. It's convergent regardless of the value of E total. And this, in fact, defines a completely entire function of E total. There's no singularities at E total goes to 0 at all. There's just nothing here. Okay. Now that might look very surprising to you. And it looks like a sort of and it is, in fact, it's a kind of it's a precise sense in which naive Wilsonian decoupling notions are just wrong. Now they're wrong for like funny questions, but they are actually wrong. I can give a more simple example. Let's say I gave you the function 1 over e, and you're an experimentalist and you've measured 1 over e and you've measured it for e positive, and you measured it to incredible accuracy, and you see it's 1 over e on the real axis, on the positive real axis. So here you measure that it's 1 over e, and your theorist friend says, aha, I know that the function is 1 over e, therefore, and it has to have a pole that equals 0, and if I do a contour integral around the origin, I'll get 2 pi I or 1. But that can be completely wrong, because the actual function can be 1 over e times 1 minus 10 to the minus 120 e over some e naught. Okay, and so if you do that, then you can see that for positive e, for positive e, there's no problem, but there's in fact no pole at e equals 0, and everything is and the function is actually totally entire. So in other words, it's possible to have something that agrees to exponentially high accuracy with what you think you get from low energy considerations on the positive real axis, while it's wildly off here. Okay, wildly off out here. Okay, so that means that all of this business that we can see the high energy amplitude in the correlation function by this k total pole, that in fact, exactly speaking, in any, and even if we don't talk about gravity, even if we have something like perturbative strings in de Sitter, even though we don't have a precise formulation for it, if we have something like perturbative strings in de Sitter, that would just mean that all these K-total singularities are not there. So, that's I think extremely interesting because on the one hand, we know the K-total singularities are not there in this analytic continuation. On the other hand, surely when we go to the folded limit, even though it's exponentially suppressed because the masses are heavy compared to Hubble, we should see these tiny oscillations with the exponentially small magnitude, e to the minus m over h magnitude, but we should see these exponentially small oscillations. And so we should see all of that non-analyticity associated with those oscillations in the squeeze limit. But while in all examples we understand perturbatively, those branch cuts extend and they end on a K-total singularity where we can identify the flat space scattering amplitude. Somehow in UV complete theories that have gravity, that can't happen. There is no branch, there's no singularity at K-total, and they just have to disappear somewhere. Where they disappear, how it works, I have no idea. But that's a very sharp challenge of UV completion. You want to come up with some kind of amplitude, which of course should have all these higher tower of higher mass objects in them. You should be able to see those objects in principle, even though exponentially small. You should be able to see them in principle in the squeeze limits, but they have to disappear and not give you anything in the K-total singularity. So that's kind of that's an analog of a problem that you can set up for amplitudes to try to sort of discover or even guess the Veneziano amplitude from the bottom up, just by something that has poles. It's soft in the correct way, and it has an interpretation on the poles of having positive residues to give you a positive probability for producing all these higher spin massive particles. That's already a very tall order to be able to do that in flat space, but then you can just plonk down the Veneziano amplitude or the Virasoro-Shapiro amplitude, and it exists. I'm saying the analog of that question exists in de Sitter, even if we can't, if someone could just magically guess this amazing formula, which has the feature that it gives us all of these, it gives us all of this tower of massive particles that we see in the squeeze limit, but miraculously no residue at all on K-total. That would be a candidate for the sort of Veneziano correlator in de Sitter.
Well,
the analog of the Veneziano correlator in ADS still doesn't really exist.
Can we discuss a little bit?
More interesting in de Sitter, precisely because the masses are big, that we really get to see all of these guys. We get to see all of them and all their oscillations, and yet they have to sort of disappear as we do this analytic continuation. So I'm just saying, it's a well-posed mathematical problem. I don't know, it's probably a very, very hard problem, but it's a well-posed problem.
Nima, can we have some discussion of this? Because I think Meredith wanted to say something, and I'd like to also.
Sure.
Yeah, Meredith, go first, though. I think you had.
Okay, I wanted to ask, it seems that this disappearance of the K-total pole, this argument based on gravity should also hold if I have a gravitational theory in Minkowski, asymptotical Minkowski. On the other hand, I thought this, on the other hand, in Minkowski, I do have the delta function of the S matrix. And I thought somehow it should, I should see it in the wave function.
What the difference is in Minkowski space, in Minkowski space, the pole on K-total gives you the actual exact scattering amplitude. Okay? Whereas the leading singularity on K-total in de Sitter gives you the high energy scattering amplitude. That is the difference. As you go back to eta, you have the sort of positive powers of eta. So what you get for the what you get, we never, from this K-total pole, we never get access to the full amplitude in cosmology. We do for the flat space wave function. In cosmology, we never get access to the full amplitude, we get access to the high energy amplitude. And it's because the high energy amplitude is exponentially small that we get this problem.
Okay, thanks.
So I wanted to make a couple comments from the top-down perspective. So de Sitter, it is complicated in this respect that you said, although there are, just for the record, there are perturbative examples. So in principle, one would do something like Fischler-Susskind. But I don't think you need the whole Veneziano amplitude. What you need is the softening effect. And those things can be seen a little bit more simply. The way that the string spreads out is, you can infer from the variance of the embedding coordinates a la Susskind, and we did verify this in the string S matrix in flat space. So those effects do the softening that you're saying without needing the full formula. So
no, I mean, there are ways of getting access to the physics. I'm saying that there's a I'm saying that there's a well-posed question for writing down a 4-point function that would come from a UV complete theory in de Sitter. Whatever the formalism is, however you want to get it, however you want to describe it, if someone handed you the formula like Veneziano did without having all the formalism, you can check whether it's right or wrong. And to check whether it's right or wrong has this fascinating component, which that you have to see the particles and not see them at the same time. You have to see them where we expect to see them in the squeeze limit and see them all disappear on the KK total singularity. That's all I'm saying.
I know, but we do have, you could run this argument at various levels. You don't have to necessarily derive this as a unique answer. Instead, you can use the crutch of knowing a UV completion that's at least very well studied.
Then I would love to see even a candidate formula that does this.
Well, look, what I'm saying is the softening effect can be clear without the full formula. That's point one. Point two, let me say, which is a little more along your lines, although of limited interest for de Sitter itself. There is a solvable theory called the time-like linear dilaton theory, where the full generalization of the Veneziano amplitudes are known. In that case, you have to be careful and introduce wave packets because the coupling is increasing in one direction, the past. But those formulas exist. We worked them out as part of the S matrix study of string spreading, and it goes back further. And there, you have some similar formulas with linear contributions and momenta in the denominator, and the softening of string theory is in those formulas, and they are very explicit. So if you're interested in general FRW, that would be an example where indeed the stringy stuff is computable and has been computed.
Okay, I'd be very interested in seeing what the actual formulas look like. I mean, my understanding, even in ADS, where this was done by Wan and Hiroshi, I think the analog of what you're talking about, they're very implicit. The formulas are quite implicit. In
this case, I know what you mean. In this case, it's actually easier because, as you know, maybe not everyone knows, the theory here is a Gaussian theory. It just has an improved stress energy tensor. So, as you might imagine, the formulas are simple. And what goes to Mehrdad's question about what happens to the delta function is, you have to put in a wave packet, and the usual delta function comes from integrating out the zero mode in the embedding space. And here, you can do that integral, but you get a different answer from the delta function. But it's that's you can see where the would have been delta function goes. And again, this is not de Sitter, although it's interesting because in Einstein, in the correct frame, let's say it's on the verge of accelerating. It's not quite there. It's A of t equals t. So.
Okay, I'd be very interested in seeing that. I haven't seen that. I didn't know that there was something relatively explicit. Right. Okay. So
can I ask you a quick question?
Yes.
Yeah, so I'm wondering why I think you tried to solve the Big Bang singularity and when eta goes to 0, but I'm not sure if at that limit necessarily the space-time is de Sitter. My understanding is that we have this very short time of quasi de Sitter during inflation, but not before that. Am I missing something? Thanks.
No, in fact, this may be my final point. So maybe I'll just say this final point very, very quickly, and then we can come back. So let's go back to this example. Let's say in principle we want to know how is the physics of the sort of heavy modes that are regulating gravity and de Sitter, which should even be the same as what are regulating things naively in flat space, the ultraviolet stuff. How do we see that physics in the boundary correlate? And let's imagine, let's forget at zeroth order about the fact that our universe is accelerating, so we have a horizon and cosmic variance and all that stuff. Let's just forget that and imagine that we're opening up into flat space. Then we know how we would do it. In principle, we would measure these correlators, and these tiny exponentially small things which are there are the signal of the real UV things that are actually doing the UV completion for us. As I said, the fact that they're tiny and exponential on one end doesn't mean that their consistency isn't important, because somehow when you analytically continue, they have to magically conspire to give me 0 on the K total pole. So they're exponentially tiny in the physical regime, but they become important under the various analytic continuation. What I want to say is that in principle, you can see, if you're interested in, spin modes that are 100 times heavier than Hubble during inflation, in principle, you could measure e to the minus 100 level effects and see them. Ditto for what happened at the Big Bang singularity. This is just, let's say, there you might have to go further. We might have had many e-folds of inflation. But let's say you're just a very dumb, simple-minded person. You just put some cutoff at near eta equals 0. So brick wall, someone else has a different cutoff. You make some assumption about what the modes look like. You trace what those assumptions do to the correlators at very late times. And in principle, they matter. They're exponentially tiny, but in principle, they matter. So in principle, you could decide whose theory is right or wrong based on these exponentially tiny things that you could measure. What bothers me is that our current epoch of acceleration actually makes that, even in principle, impossible because of cosmic variance. And this is now much worse than the usual things we talk about being imprecise in de Sitter. Normally we say everything is imprecise in de Sitter at order, e to the minus 10 to the 120, because it's a finite system with finitely many degrees of freedom, blah, blah, blah. But that's incredibly academic. It's very conceptually important, but it's incredibly academic, because much before that, I would worry about the fact that me as a finite human being made out of 10 to the 30 degrees of freedom can't talk about anything to accuracy better than e to the minus 10 to the 30. So that e to the minus 10 to the 30 whomps the e to the minus 10 to the 120 from the fact that we live in de Sitter. However, this is a question that I could care about in principle. I could imagine it attempting to measure some correlator to accuracy e to the minus 1,000 to pick out the oscillations associated with heavy string modes, or to pick out the possible effects of whether I put a brick wall or some other boundary conditions or whatever is going on near eta equals 0. But all of those things, all of those effects that are exponentially small in the correlator, they're all swamped by our cosmic variance today, given the fact that we have access to a finite number of modes, and that the square root of that number of modes is already much bigger than, even e to the minus 100. So I find this curious, that late acceleration, the cosmic variance associated with late acceleration puts a bound on the size of the correlations we can see that would even in principle tell us something about the presence of very massive states during inflation, or of what happens near the Big Bang singularity. I don't know what this means. Not too many people care. Of course, it's very academic, but I find it interesting that this is an aspect of late time acceleration that is much more bothersome to me than the usual things about de Sitter having finitely many degrees of freedom. It means that there is no scientific question that at least I understand that's consistent with quantum mechanics that lets us, even in principle, talk about what happened at the Big Bang, or even in principle talk about whether there were strings that were 50 times Hubble or 200 times heavier than Hubble during inflation. Late acceleration, cosmic variance associated with late acceleration erases our access to those questions. And I find it fascinating, and I don't know how to think about it. So the message of these last two things is sort of opposite. First, there's a very precise kind of nice mathematical question to try to see whether there is some kind of de Sitter-Veneziano correlators. Okay, so that's very nice. And we know there's well-posed rules for what they should do. But then there's a physical issue that none of these things associated with heavy states or the Big Bang singularity appear to be, even in principle, measurable. And how to think about that is, I think, a very interesting question. Okay, so I've gone well far enough. I didn't talk. If people are interested, I'll be happy to talk offline about what I had in mind about the emergence of bulk.
Yeah, Guy and I were proposing to kind of close the formal workshop, but let the channel open for people who want to stay longer and keep discussing. So we get the opportunity to thank everyone who participated, who submitted their contributions and who gave live talks and made it for me. It was an extremely successful workshop. I learned a ton of things. It has really broadened my horizon on what is going on. And so I wanted to thank everyone. And we're gonna keep this on so the show can continue. But if people wanna turn off, I mean, that's left to the individuals. Guy, do you wanna say something else?
No, I think that's it. Well, thank you very much for participating. This thing started as just let's have a couple of people discuss, and it ballooned to something much bigger. It was a lot of fun. I hope you enjoyed these discussions and this lack. And yeah, thanks for participating. It was a lot of fun.
Thanks, you guys. This was fantastic.
Thanks.
Oops.
Much better than being jet lagged.
Yeah, no traveling necessary. All right, I'll stop recording and then we can continue.